Question 1. Consider the function shown. Which of the following could be the equation of this function? The equations presented in all four options are in gradient-intercept form, that is y equals mx plus c, where m represents the gradient of the line and c represents the y-intercept, and that's the point where the line crosses the y-axis. Now, as a side note, the gradient or slope of a line is always determined from left to right. So looking at our line, from left to right, we can see that it's going downhill. That means the value of m must be negative. We can also see that the line crosses the y-axis at a point above the origin. That means the value of c must be positive. So by inspection, m is negative, c is positive, hence the equation could be y equals negative 2x plus 3. Therefore, the correct answer is option C. Question 2. In a group of 60 students, 38 play basketball, 35 play hockey, and 5 do not play either basketball or hockey. How many students play both basketball and hockey? I've sketched a Venn diagram for visualization. We know that there are 60 students in total, and 5 do not play a sport. So 60 minus 5 leaves us 55 students that play either basketball and or hockey. So in other words, 55 students have to be within either one of these two circles or both. And the question is asking for the number of students that play both basketball and hockey. In other words, the number of students that are in the intersection of the two circles. Now it's given that 38 students play basketball and 35 students play hockey. So 38 plus 35 gives us 73, but there are 55 physical students. That means some students must play both sports. So 73 minus 55 gives us 18. So there are 18 students that are in the intersection of both circles. Therefore, the correct answer is option B. Question 3. Pia's marks in Year 10 assessments are shown. The scores for each subject were normally distributed. In which subject did Pia perform best in comparison with the rest of Year 10? We want to find the subject with the largest number of standard deviations relative to the mean. Now, since the data is normally distributed, we can use the z-score formula, z equals x minus mu over sigma, where x represents Pia's mark in that subject, mu represents the mean mark in that subject, and sigma represents the standard deviation of marks in that subject, to compare all four subjects and then find the subject with the highest z-score. So let's look at English. The z-score for English is z equals 78 minus 66 in brackets, dividing that by its standard deviation, which is 6, and that gives us a z-score of 2. Looking at mathematics, z equals 80 minus 71 in brackets divided by 10, we get a z-score of 0.9. Looking at science, we have z equals 77 minus 70 in brackets divided by 15, we get a z-score of approximately 0.4666 and so on. And looking at history, we have z equals 85 minus 72 in brackets divided by 9, and we get a z-score of approximately 1.444. So comparing all four z-scores, we can clearly see that English has the highest z-score of 2. So Pia performed, relatively speaking, the best in English. So the subject with the highest z-score indicates the best relative performance to the mean, which is English. Therefore, the correct answer is option A. Question 4. The parabola y equals x minus 3 in brackets to the power of 2 minus 2 is reflected about the y-axis. This is then reflected about the x-axis. What is the equation of the resulting parabola? The original parabola is y equals x minus 3 in brackets squared minus 2. Now we're going to reflect this parabola in the y-axis by replacing the x variable with negative x. What that means is every point that makes up that curve, the x coordinates change sign. So whatever was positive to begin with becomes negative, and whatever was negative to begin with becomes positive. So just think that all the x coordinates change sign. So the parabola becomes y equals negative x minus 3 in brackets squared minus 2. We'll factorize out the negative later on, so we'll leave it in that form for the time being. Next, reflect this parabola here in the x-axis by replacing y with negative y. Again, for the same reason, all the y coordinates of the points that make up that curve change sign. So whatever was positive becomes negative, and whatever was negative becomes positive. So in other words, negative y is equal to negative x minus 3 in brackets squared minus 2. But we don't want negative y. So let's multiply both sides of the equation by negative 1 to bring the negative y back to y. So the equation becomes y equals negative, open bracket, negative x minus 3, close bracket squared, plus 2. Now we can factorize the negative from the x and the 3 inside this bracket here. So the equation becomes y equals negative, open bracket, negative, open bracket, x plus 3, close bracket squared, plus 2. So all I've done is I've just taken the negative out, and the x minus 3 or negative x minus 3 becomes x plus 3. Now just as a side note, negative, let's say negative u in brackets squared is identical to u squared. Since we're squaring a negative, the two negatives cancel and become positive. In this case, u is equal to x plus 3. So what we end up with is y is equal to negative, open bracket, x plus 3, close bracket squared, plus 2. Therefore, the correct answer is option C. Question 5. What is the indefinite integral of 6x plus 1 in brackets to the power of 3 dx? Integrating expressions of the form ax plus b in brackets to the power of n involves raising the power by 1. So in this case, the n becomes n plus 1. We then divide by the new power, but we also have to divide by the derivative of what's in the brackets. So the derivative of ax plus b is a. So integrating ax plus b in brackets to the power of n gives us ax plus b in brackets to the power of n plus 1 divided by n plus 1 divided by a, which can be written as 1 over a times n plus 1 in brackets times ax plus b in brackets to the power of n plus 1. Hence, the integral of 6x plus 1 in brackets to the power of 3 dx is equal to 1 over 24. So we're dividing by 4 and then dividing by 6, which is the same as dividing by 24, or multiplying by 1 over 24 times 6x plus 1 in brackets to the power of 4 plus the constant of integration c. Therefore, the correct answer is option A. Question 6. What is the domain of the function f of x equals 1 over the square root of x squared minus 1? Since division by 0 is undefined, the denominator of the fraction, the square root of x squared minus 1, cannot equal 0. Hence, x cannot equal positive or negative 1. This rules out options A and B. Now, what's inside the surd, x squared minus 1, has to be greater than or equal to 0, or else we'll be taking the square root of a negative value. This implies that x squared has to be greater than or equal to 1. Solving this inequality, we have either x is greater than or equal to 1 or x is less than or equal to negative 1. but x cannot equal positive or negative 1 from this condition here. Therefore, the correct answer is option D. Question 7. The diagram shows the graph y equals f of x. Which of the following best represents the graph y equals f of 2x minus 1? Start by expressing the function such that the variable x is monic, and we do that by factorising out 2 from 2x and negative 1. So the function can be written as f of 2 times x minus 1 over 2 in brackets. Next, follow Dr. T. That is, consider the dilations, then the reflections, and then the translations in that order. Now, the 2 here means dilate the curve horizontally by factor 1 over 2. In other words, squeeze or compress the curve toward the y-axis. This minus 1 over 2 means translate the curve to the right by half a unit. Therefore, the correct answer is option C. And for completeness, let's have a look at the original graph and consider the two transformations in order. So what we're doing is squeezing or compressing the curve toward the y-axis, a bit like an accordion, and then moving the entire curve over to the right-hand side by half a unit. And that's why the correct answer is option C. Question 8. Some data are used to create a box plot as shown. A histogram is created from the same set of data. Which of the following histograms is not possible for the given box plot? Recall that each of the 4 components of a box plot represent 25% of the data. Now, in this particular box plot, what we notice is that the 2 tails are relatively short compared to the 2 rectangles that make up the box. This implies that there is a concentration of data at the endpoints, or where the tails are. As far as the histogram is concerned, that is reflected in the taller columns at each end of the histogram. So if we take option A, we can see a concentration of data here and here, given the taller columns here and here. Same thing with option B. We see a concentration of data here and here, which corresponds to the tails. Same thing with option C. We can see a concentration of data here and here, which again corresponds to the tails. However, with option D, we can see a concentration of data in the center. So with option D, this histogram implies the tails are quite long, but the box component is quite narrow. Therefore, the histogram in option D is not possible for the given box plot. Question 9. A bag contains 2 red and 3 white marbles. Jovan randomly selects 2 marbles at the same time from this bag. The probability tree diagram shows the probabilities for each of the outcomes. Given that one of the marbles that Jovan has selected is red, what is the probability that the other marble that he has selected is also red? I calculated the probabilities of all 4 outcomes by multiplying along the branches of the probability tree. So the probability of red is 2 over 5 times 1 over 4, which gives us 1 over 10. Now I've calculated all 4 outcomes in a similar way. So the probability of red white is 3 over 10, the probability of white red is 3 over 10, and the probability of white white is 3 over 10. Now this is the case of conditional probability. We know that one of the marbles selected was red. That means the outcome white white could not have happened. So what we're going to do is to restrict the sample space by not considering this particular path. So in other words, The probabilities that we're considering are these three probabilities or these three outcomes because they all involve at least one red marble. Now, if one red marble was chosen, we want to find the probability that the other marble chosen was also red. So in other words, we want the probability of red given that this particular outcome, white, did not happen. And the way we work that out is we take the probability of red and then divide it by the probabilities of the three outcomes that involve at least one red marble. So that's 1 over 10 plus 3 over 10 plus 3 over 10, which is 7 over 10. So the probability of red given that one red marble was chosen is 1 over 10 divided by 7 over 10, which gives us 1 over 7. Therefore, the correct answer is option B. Question 10. The diagram shows the graph y equals f of x. The point Q is a horizontal point of inflection. Let a of x equal the integral from 0 to x of f of t dt. How many points of inflection does the graph y equals a of x have? Let's reframe the question so we are not making direct reference to the integral here. In other words, let's make it in terms of f of x and f dash of x rather than f of x and the integral of f of x. The diagram shows the graph y equals f dash of x. The point Q is a horizontal point of inflection. How many points of inflection does the graph y equals f of x have? As a side note, f of x is a primitive of f dash of x. We differentiate f of x to get f dash of x. But if we're given f dash of x, we integrate f dash of x to get back to f of x. Going back to the graph of y equals f dash of x, the y values represent the gradient of the tangent at the corresponding x values on the graph y equals f of x. So this point here, this point here, this point here, this point here, there's 4 x-intercepts. They represent stationary points on the curve y equals f of x, and there are 4 of them. But we're interested in the points of inflection. Now, points of inflection mark a change in concavity. So if we consider the graph of y equals f of x, an inflection point will mark a change from either concave up to concave down or concave down to concave up. This means that the value of the second derivative changes sign on either side of the point of inflection, but it also means that the first derivative must stay the same sign on either side of the point of inflection. I've sketched a part of y equals f of x here, which corresponds to this stationary point here on the curve y equals f dash of x. Now the y value is negative, which means the gradient of the tangent at the corresponding x value on y equals f of x is negative. In fact, it's most negative here. But if we move away from this point here, we can see that the y value on y equals f dash of x approaches 0 as we move away from this point here. But it's negative on either side, regardless. So the sign of f dash of x is negative on either side. So this point here corresponds to a point of inflection on the curve y equals f of x. Now point Q is a bit of a distractor. If we look at point Q, the y value to the left of point Q is negative, but the y value to the right of point Q is positive. So this can't be a point of inflection on the curve y equals f of x. Now, for similar reasons to what I explained here, this point here corresponds to an inflection point on the curve y equals f of x, and also this point here. Therefore, there are 3 points of inflection on the curve y equals f of x. If we go back to the wording of the original question, how many points of inflection does the graph y equals a of x have? The correct answer is 3. Question 11. The graph of the function g of x is shown. Using the graph, complete the table with the words positive, 0 or negative as appropriate. Let's look at the sign of the first derivative g dash of x at the points where x equals negative 3, x equals 1 and x equals 5. If we look at the gradient of the tangent at those 3 points, at x equals negative 3, the gradient of the tangent is positive. So the first derivative g dash of x is greater than 0, so it's positive. At x equals 1, this is a horizontal inflection point. The gradient of the tangent is 0, so g dash of x, the first derivative, is 0. And at x equals 5, the gradient of the tangent is positive. So the first derivative, g dash of x, is positive. Let's look at the second derivative around those points. At x equals negative 3, the curve is concave down. So the second derivative, g double dash of x, is less than 0, so it's negative. At x equals 1, this is an inflection point. So g double dash of x, the second derivative, is equal to 0. And at x equals 5, the curve is concave up. So g double dash of x is greater than 0, so the second derivative is positive. Completing the table, the results are summarized there. At x equals negative 3, the first derivative is positive, the second derivative is negative. At x equals 1, the first derivative is 0 and the second derivative is 0. And at x equals 5, the first derivative is positive and the second derivative is positive. Question 12. Find the sum of the terms in the arithmetic series 50 plus 57 plus 64 and so on through to 2024. In the given arithmetic series, the first term a is equal to 50 and the common difference d is equal to 7. That's the difference between successive terms of this series. In other words, what do we need to add to a particular term to get to the next term? Hence why the common difference is 7. Now we need to find the value of n that corresponds to the last term, 2024. So using the formula Tn is equal to a plus n minus 1 in brackets times d, this gives us the value of the term at position n. We know that the value at position n is 2024, and that's equal to 50 plus n minus 1 in brackets times 7. And we need to solve this equation for n. Now subtracting 50 from 2024, we get 1974 is equal to n minus 1 in brackets times 7. Dividing 1974 by 7 to isolate n minus 1, we get n minus 1 is equal to 282, hence n is equal to 283. This means there are 283 terms from 50 to 2024. Now to find the sum, we can use the formula Sn is equal to n over 2 times a plus l in brackets, where l is the last term of the series. So S 283, that's the sum of the first 283 terms of this series, is given by 283 over 2 times 50 plus 2024 in brackets, and that equals 293,471. Question 13. The graph shows the populations of two different animals, W and K, in a conservation park over time. The y-axis is the size of the population and the x-axis is the number of years since 1985. Population W is modelled by the equation y equals a times 1.055 to the power of x. Population K is modelled by the equation y equals b times 0.97 to the power of x. Complete the table using the information provided. Both equations are instances of exponential functions because the index in both equations is the independent variable x. Now x represents the number of years since 1985. Let's look at population W. It's modelled by the equation y equals a times 1.055 to the power of x. Notice that the base is greater than 1. What that means, as x gets larger, y will get larger. So population W is increasing as time goes on. And it's modelled by this curve here on the graph. And I've labelled it here with a W. Population K has a base that's less than 1 but greater than 0. As x gets larger, y is getting smaller. So the population of K is decreasing over time. And I've labelled that as such. Now when x is 0, 1.055 to the power of 0 is equal to 1. That means in 1985, y is equal to a, and that represents the initial population for population W. Same thing goes for population K. When x is 0, that represents the year 1985. 0.97 to the power of 0 is 1, so y is equal to b, and that represents the initial population of population K. And that corresponds to the y-intercepts of both curves. So here's A here, and here's B. So let's proceed to complete the table. Now it's given that the initial population in 1985 for population W is 34, and that corresponds to the y-intercept here. Now, if we look at the y-intercept for population K, so that's this decreasing curve, at this point here, it corresponds to 280. Let's look at the percentage yearly change in the population. And we consider the bases of both exponential equations, which I'll go back to the original equation. So the base for population W is 1.055. And that can be written in percentage form as 100% plus 5.5%. So if you add those two together and convert it to decimal, we get 1.055. And that corresponds to a 5.5% percentage yearly change in the population. And I've noted that here. Now the base for population K is 0.97. In percentage form, that can be written as 100% minus 3%. We do know that population K is in fact decreasing, and that corresponds to a negative 3% decrease each year. Lastly, to find the predicted population for population W, we can use the equation. So we have y is equal to a times 1.055 to the power of x. So when x is 50, we substitute 50 for x here. And we know the value of a, which is 34. So when x is 50, y is equal to 34 times 1.055 to the power of 50, which equals 494.4266 and so on, which rounds to 494, correct to the nearest whole number. And I've written that here. Question 14. The curves y equals x minus 1 in brackets squared and y equals 5 minus x squared intersect at 2 points as shown in the diagram. Part A. Find the x coordinates of the points of intersection of the two curves. Find the x coordinates of the points of intersection by solving simultaneously the equations y equals x minus 1 in brackets squared and y equals 5 minus x squared. Now, because the left-hand side of both equations is the same variable, the variable y, we can equate the right-hand side of both equations, effectively using the substitution method of solving simultaneous equations. So x minus 1 in brackets squared is equal to 5 minus x squared. Expanding the left-hand side, we get x squared minus 2x plus 1 is equal to 5 minus x squared. Moving the terms on the right-hand side over to the left-hand side and collecting like terms, we get 2x squared minus 2x minus 4 equals 0. Now this is a non-monic quadratic equation, but it also happens that the coefficients of x squared, x, and the constant term are even numbers. So we can divide all terms by 2 and we get x squared minus x minus 2 is equal to 0. This is a monic quadratic equation, which is certainly easier to solve. In fact, by inspection, we can factorize the left-hand side. We get x plus 1 in brackets times x minus 2 in brackets is equal to 0. That is, we need to find two numbers whose sum is negative 1 and whose product is negative 2. So positive 1 and negative 2 will work in this case. So from the left-hand side, from these two factors, we have the x coordinates of the points of intersection are x equals negative 1 and x equals 2. Part B. Find the area enclosed by the two curves. The area between the two curves is the difference in the area between the concave down parabola and the concave up parabola between the 2 points of intersection that we've found in part A. So that's from x equals negative 1 to x equals 2. So to find the area, we integrate both curves. And notice that we start off with the concave down parabola because between x equals negative 1 and x equals 2, the concave down parabola is above the concave up parabola. So the area A is given by the integral from x equals negative 1 to x equals 2 of 5 minus x squared minus x minus 1 in brackets squared dx. Expanding this bracket here using perfect square expansion, we get the area is equal to the integral from x equals negative 1 to x equals 2 of 5 minus x squared minus open bracket x squared minus 2x plus 1 close bracket dx. It's important to keep the expansion in brackets for now. In the next step, I'm going to expand this bracket here. So this negative will be multiplying all terms inside this bracket there. So expanding the brackets, we get the area is equal to the integral from x equals negative 1 to x equals 2 of 5 minus x squared plus 2x minus 1 dx. Collecting the like terms, the integrand becomes 4 plus 2x minus 2x squared. Notice that all three terms of the integrand are divisible by 2. So factorizing out 2, placing it outside of the integral, which will make the integration a little easier, we get the area is given by 2 times the integral from x equals negative 1 to x equals 2 of 2 plus x minus x squared dx. So integrating this expression here and noting this 2 that's multiplying the integral, we get 2 times 2x plus x squared over 2 minus x cubed over 3 from x equals negative 1 to x equals 2. So applying the limits of integration, we get 2 times, I'm going to open square bracket here and open round bracket, 2 times 2 plus 2 squared over 2 minus 2 cubed over 3, close round bracket, minus open round bracket, 2 times negative 1 plus negative 1 in brackets squared over 2, minus negative 1 in brackets cubed over 3, and we're closing the brackets here. So evaluating what's inside the round brackets, we get 2 times 10 over 3 minus negative 7 over 6. and that evaluates to 9. Therefore, the area is 9 square units. Question 15. Initially, there are 350 litres of water in a tank. Water starts flowing into the tank. The rate of increase of the volume V of water in litres is given by dV dt equals 300 minus 7.5 t, where t is the time in hours. Find the volume of water in the tank when dV dt equals 0. I'm going to start by solving dV dt equals 0 because we need to know at what point in time is the rate of change of volume equal to 0. So solving 300 minus 7.5t equals 0, rearranging this equation to make negative 7.5t the subject, so we just move the 300 over to the other side, it becomes negative 300, dividing both sides of the equation by the coefficient of t, so dividing by negative 7.5, we get t is equal to 40. Hence, dV dt is equal to 0 at time t equals 40 hours. Now the volume V of water is given by V equals the integral from t equals 0 to t equals 40 of 300 minus 7.5t dt plus 350. If you recall, initially there's 350 litres of water in the tank. So performing the integration, we get 300t minus 7.5t squared over 2 from t equals 0 to t equals 40 plus 350. Applying the limits of integration, we get 300 times 40 minus 7.5 times 40 squared over 2 minus 0 plus 350, which evaluates to 6,350. Therefore, the volume of water in the tank when dV dt equals 0 is 6,350 litres. Question 16. Flowers were planted in 2 gardens, Garden A and Garden B. On a particular day, 25 flowers were randomly selected from each garden and their heights measured in millimetres. The data are represented in parallel box plots. Compare the 2 data sets by examining the skewness of the distributions and the measures of central tendency and spread. Comparing the skewness of the distributions, we can observe that the left-hand tail for the box plot for Garden A is much longer than the right-hand tail. In contrast with Garden B, the left-hand tail is much shorter than the right-hand tail for Garden B. This means that the distribution of Garden A is negatively skewed, so most of the data is stacked on the positive side with a tail on the negative side. In contrast with Garden B, most of the data is stacked on the left-hand side or the negative side, and there's a tail on the positive side. And I've written that down as our first point. So data set for Garden A is negatively skewed, while data set for Garden B is positively skewed. Looking at the range and the interquartile range for both gardens, we can see that the range for Garden A is bigger than the range for Garden B. Also, the interquartile range, so that's between quartile 1 and quartile 3, the interquartile range for Garden A is also larger than the interquartile range for Garden B. And I've written that as the second point. So the range and interquartile range for garden A is larger than the range and interquartile range for garden B. Finally, examining the measures of central tendency, we can compare the medians. So looking at the two median lines in both box plots, we can see that the median for garden A is much larger than the median for garden B. And I've written that as the third and final point. The median for garden A is larger than the median for garden B. Question 17. In a particular electrical circuit, the voltage V, volts, across a capacitor is given by V of t equals 6.5 times 1 minus e to the power of negative kt in brackets, where k is a positive constant and t is the number of seconds after the circuit is switched on. Part A. Draw a sketch of the graph of V of t showing its behaviour as t increases. Let t equal 0 to find the initial voltage on the capacitor, and that will be our starting point when drawing the graph. So the value of V of 0, which represents our initial voltage, is equal to 6.5 times 1 minus e to the power of 0 in brackets. Now e to the power of 0 is equal to 1, and 1 minus 1 is equal to 0, and 6.5 times 0 is equal to 0. So V of 0 is equal to 0, and that represents the starting point of our graph. Let's see what happens as t approaches infinity. In other words, as time gets larger and larger, or as we progress further and further in time, let's see what happens to e to the power of negative kt. Now k is positive, so we have a negative here, so a negative positive, which makes a negative, multiplied by a large value of t. Effectively, what we're doing is e to the power of negative infinity. So as t gets bigger and bigger, e to the power of negative kt gets smaller and smaller, in the sense that it gets closer and closer to 0. So if we think about it in terms of limits, the limit as t approaches infinity of e to the power of negative kt is equal to 0. Hence, v of t approaches 6.5 as t approaches infinity, because this e to the power of negative kt approaches 0, which is this term here, and then we're just left with the 1. So 6.5 times 1 is just 6.5, and that's why v of t approaches 6.5 as t approaches infinity. And that is in fact our horizontal asymptote on the graph. Now it's a negative exponential graph in the sense that it rises more rapidly in the beginning, but then it shallows out, and the gradient of the tangent on this curve approaches 0 as we get closer and closer to the horizontal asymptote. So here's the graph, here's our origin, there's the horizontal axis, which is time, our vertical axis, which is voltage, V of t, and the horizontal asymptote needs to be clearly marked at 6.5, and the curve should approach the asymptote but never touch it, as so. Part B. When t equals 1, the voltage across the capacitor is 2.6 volts. Find the value of k, correct to 3 decimal places. We are given that V of 1 is equal to 2.6. In other words, when t equals 1, the voltage across the capacitor is 2.6 volts. Hence, we can form the equation 2.6 is equal to 6.5 times 1 minus e to the power of negative k times 1 in brackets. Now, negative k times 1 is negative k, and we can divide 2.6 by 6.5 and we get 0.4. So the equation simplifies to 0.4 equals 1 minus e to the power of negative k. Subtracting 1 from 0.4, we get negative 0.6 is equal to negative e to the power of negative k. And we can rewrite that as e to the power of negative k equals 0.6. Since we have a negative here and a negative there, if we divide by -1, the 0.6 here becomes a positive, and the e to the power of negative k also becomes a positive. Now we have base e here. We want to solve for k, so we can take the natural logarithm of both sides of the equation. So we get ln of e to the power of negative k is equal to ln of 0.6. So simplifying the left-hand side, we get negative k, and that's equal to ln of 0.6. Dividing both sides of the equation by -1, so we can isolate the k, we get k is equal to negative ln of 0.6, which evaluates to 0.5108256 and so on. But the question is asking for the value of k correct to 3 decimal places. Therefore, k is equal to 0.511 correct to 3 decimal places. Part C. Find the rate at which the voltage is increasing when t equals 2, correct to 3 decimal places. Part C is asking for an instantaneous rate of change of voltage with respect to time. So we will need to differentiate the voltage equation V of t equals 6.5 times 1 minus e to the power of negative kt in brackets with respect to t. To make the differentiation a little easier, we can expand the brackets first. So V of t is equal to 6.5 minus 6.5 e to the power of negative kt. Now we can differentiate V of t with respect to t. Now the derivative of a constant, so in this case 6.5, is 0. So we only have to differentiate negative 6.5 e to the power of negative kt. So applying the chain rule, V dash of t, which represents our first derivative, is equal to negative 6.5 times e to the power of negative kt times the derivative of the index with respect to time, or with respect to t. So we're multiplying that by negative k. And that simplifies to 6.5 times k times e to the power of negative kt, where k is equal to 0.511, which we found in part A. So to find the rate of change of voltage across the capacitor at the 2-second mark, we substitute 2 for t in the first derivative here. So V dash of 2 is equal to 6.5 times 0.511 times e to the power of negative 0.511 times 2, which evaluates to 1.195323 and so on. Now the question is asking for the rate of change correct to 3 decimal places. So this rounds to 1.195. Therefore, the voltage is increasing at the rate of 1.195 volts per second at time t equals 2. Question 18. In a game, the probability that a particular player scores a goal at each attempt is 0.15. Part A. What is the probability that this player does not score a goal in the first 2 attempts? Firstly, events are independent. So that means scoring a goal in one attempt will not affect the probability of scoring a goal in subsequent attempts. Also, the probability of not scoring a goal in an attempt is the opposite or the complement of scoring a goal in an attempt. Now, it's given that the probability of scoring a goal is 0.15 or 15%. So the probability of not scoring is 1 minus 0.15 or 100% minus 15%, which gives us 85% or 0.85. So the probability of not scoring twice is 0.85 times 0.85, And that's why I stated earlier that the events are independent, so all we have to do is multiply the two probabilities together. So 0.85 times 0.85 or 0.85 to the power of 2 equals 0.7225. Part B. Determine the least number of attempts that this player must make so that the probability of scoring at least one goal is greater than 0.8. We want to find an integer value of n such that the probability of scoring at least one goal in n attempts is greater than 0.8 or 80%. Now that's the equivalent of stating the probability of scoring no goals in n attempts being less than 0.2 using the law of complements. So in effect, what we want to do is solve the inequality 0.85 to the power of n less than 0.2. That's going by this statement here. So we want to find a value of n such that 0.85 to the power of n is less than 20%. Now we need to isolate the n, so we take the natural logarithm of both sides, and then the n just comes out to the front. So n times ln of 0.85 is less than ln of 0.2. Now ln of 0.85 is a negative value, so dividing both sides of the inequality by ln 0.85, we need to flip or switch the inequality sign. So n is greater than ln of 0.2 divided by ln of 0.85. And evaluating the right hand side, we get n is greater than 9.903 and so on. So rounding that up to the nearest integer, we get the least number of attempts is 10. Question 19. Sketch the curve y equals x to the power of 4 minus 2x cubed plus 2 by first finding all stationary points, checking their nature, and finding the points of inflection. Find the x coordinates of any stationary points by solving the equation y dash equals 0, where y dash represents the first derivative. Now it's given that y is equal to x to the power of 4 minus 2x cubed plus 2. So differentiating y with respect to x, we get y dash is equal to 4x cubed minus 6x squared. So we want to solve for x, 4x cubed minus 6x squared equals 0. Dividing all terms by 2 to simplify the equation somewhat, we get 2x cubed minus 3x squared equals 0. Factorising out x squared from both terms on the left-hand side, we get x squared times 2x minus 3 in brackets equals 0. Therefore, x is equal to 0 or 3 over 2. Next, we find the corresponding y coordinates of the stationary points we just found. So when x is equal to 0, substituting 0 into the original equation, we get y is equal to 2. And when x is equal to 3 over 2, we get y equals 5 over 16 or 0.3125 as a decimal. Next, we determine the nature of the stationary points, and for that we can use the second derivative y double dash. So differentiating the first derivative, and we found the first derivative up here, y dash is equal to 4x cubed minus 6x squared. So differentiating that another time or a second time with respect to x, we get y double dash is equal to 12x squared minus 12x. Now when x is equal to 0, the second derivative, y double dash, is also equal to 0. That means that the stationary point at the point where x equals 0 is a possible point of inflection. So it could be a horizontal inflection point. So when x is equal to 3 over 2, y double dash is equal to 9, which is positive. So around the point where x is equal to 3 over 2, the curve is concave up. Therefore, there's a minimum stationary point around the point where x is equal to 3 over 2. So finding points of inflection by solving the equation y double dash equals 0. Now from before we found y double dash, which was 12x squared minus 12x, and we're going to solve that equaling 0. We can divide all terms by 12, we get x squared minus x equals 0. Factorising out x from the left hand side, we get x times x minus 1 in brackets equals 0. Therefore x is equal to 0 or 1. Hence we have possible points of inflection at x equals 0 or 1. We also need to find the y values at those points. So at x equals 0, y is equal to 2, which we found before. And at x is equal to 1, y is equal to 1. But we need to test these points of inflection, so to make sure that they are in fact points of inflection. And we can do that by checking for a sign change in the second derivative y double dash around those possible points of inflection. So we know when x is equal to 0, y double dash is equal to 0. When x is equal to 1, y double dash is equal to 0. But testing around those points, and I've chosen x equals -1, x equals 1 over 2, and x equals 2. At x equals -1, the value of y double dash is equal to 24, so the curve is concave up there. When x is equal to 1 over 2, y double dash is equal to -3, so it's concave down there. And when x is equal to 2, y double dash is equal to 24, so it's concave up there. So we have a sign change, positive, 0, negative, 0, positive. Hence, the point 0, 2 and 1, 1 are points of inflection, and the point 0, 2 is also a stationary point. Now we need to graph y equals x to the power of 4 minus 2x cubed plus 2. Now y is a polynomial with degree 4, so it's an even degree. Hence, y approaches infinity. In other words, y gets really large in the positive direction as x approaches either plus or minus infinity. So as we move further away from the origin, either to the right-hand side or to the left-hand side, the y values get larger on either side. So we should have two arrows at each end of this graph pointing upwards. And we know that also because the leading term, which is the x to the power of 4 term, is also positive. In other words, the coefficient multiplying x to the power of 4 is positive, which is why the two arrows on the endpoints here point upwards. If the leading term was negative, the graph would be the other way around. These arrows would be pointing downwards instead. So here is a sketch of the curve y equals x to the power of 4 minus 2x cubed plus 2. Draw the axes with a ruler. Try and make sure that the y-axis and the x-axis are perpendicular to each other. Clearly mark the origin, the x-axis and the y-axis, and I've marked in the 3 points that we found. So we have our horizontal point of inflection here at 0, 2, which is also the y-intercept. We have the other point of inflection at 1, 1, and we have the local minimum point at 1.5 or 3 over 2, 0.3125. Question 20. A vertical tower, TC, is 40 meters high. The point A is due east of the base of the tower, C. The angle of elevation to the top, T, of the tower from A is 35 degrees. A second point B is on a different bearing from the tower as shown. The angle of elevation to the top of the tower from B is 30 degrees. The points A and B are 100 meters apart. Part A. Show that distance AC is 57.13 meters, correct to 2 decimal places. Consider right angle triangle TCA, where the right angle is angle TCA. We have a known angle here, 35 degrees. We have a known side, TC, which is opposite the known angle, and we want to find the distance or the length of AC, which is the side that's adjacent to the known angle. So using SOHCAHTOA, or regular right angle trigonometry, tan 35 degrees is equal to opposite divided by adjacent, so 40 divided by AC, and I've written the working out here to reflect that. 40 divided by AC is equal to tan 35 degrees. Rearranging this equation to make AC the subject, we get AC is equal to 40 divided by tan 35 degrees, which evaluates to 57.12592 and so on. Rounding this value correct to 2 decimal places, we get AC is equal to 57.13 meters as required. Part B. Find the bearing of B from C to the nearest degree. It's given that point A is due east of point C, so the bearing of point A is 090 degrees. Now the question is asking for the bearing of point B from point C. Knowing the bearing of point A, if we can get this angle here, angle BCA, add it to 90 degrees, we get the bearing of B from C. So we need the length of BC. We know the length of AC, which we found in part A. Now I've already worked this out, length BC to be 69.28 meters. I'll go through the working out shortly. We need to consider triangle BCA. Now that's a non-right angle triangle. We have 3 known sides, so we'll need to use the cosine rule to find this angle here, angle BCA. Let's go through the working out. So similar to part A, the length BC is equal to 40 divided by tan 30 degrees, and that gives us 69.28 meters correct to 2 decimal places. In non-right angle triangle ABC, using the cosine rule, we have 100 squared is equal to 69.28 squared plus 57.13 squared minus 2 times 69.28 times 57.13 times cos angle ACB. Now I'm going to rearrange this equation here eventually to isolate cos angle ACB and then angle ACB itself. So I'm going to do that over a few steps. So first step in rearranging this equation, I've got 100 squared minus 69.28 squared minus 57.13 squared. So that's these two terms here on the right hand side. I've moved them over to the left hand side. And that equals negative 2 times 69.28 times 57.13 times cos angle ACB. Isolating cos angle ACB, we get cos angle ACB equals, open bracket, 100 squared minus 69.28 squared minus 57.13 squared, close bracket, divided by, open bracket, negative 2 times 69.28 times 57.13, close bracket, and that equals negative 0.24462626176. Taking the inverse cos or arc cos of this value here, we get angle ACB is equal to 104.1597 and so on degrees. So the bearing of B from C is equal to 90 degrees, which is the bearing of A from C, plus 104.1597 degrees, and that equals 194 degrees correct to the nearest degree. Question 21. A researcher is studying anacondas, a type of snake. A dataset recording the age, in years, and length, in centimeters, of female and male anacondas is displayed on the graph. Anacondas reach maturity at about 4 years of age. Write 3 observations about anacondas that may be made from the scatter plot. Note, no calculations are required. Some observations may include, at any given age, female anacondas are longer than male anacondas. A second point could be that male anacondas don't grow much longer after the 4th year, so that's around maturity. The rate of growth slows down significantly, whereby female anacondas tend to continue growing at roughly the same rate. A third point could be that male and female anacondas are roughly the same length at birth. Female anacondas are slightly longer. But at the 10-year mark, female anacondas are significantly longer than male anacondas. And that's by virtue of the second point, that male anacondas don't grow much longer after the 4th year, whereby female anacondas continue to grow at roughly the same rate. Question 22. The graph of the function f of x equals ln of 1 plus x squared is shown. Part A. Prove that f of x is concave up for x greater than negative 1 and less than 1. If the second derivative f double dash of x is positive or greater than 0 in the interval provided, in this case x between negative 1 and 1, then f of x is concave up in that interval. Recall that f of x is equal to ln of 1 plus x squared. So we need to use the chain rule to find the derivative of this function. Recall that the derivative with respect to x of ln of g of x is equal to g dash of x over g of x. In this case, our g of x is 1 plus x squared. So g dash of x is 2x. So f dash of x, our first derivative, is equal to 2x over 1 plus x squared. So our first derivative is a fraction where the numerator and the denominator involve functions of x. So we need to use the quotient rule to find the second derivative f double dash of x. So differentiating f dash of x, using the quotient rule, that's u dash v minus uv dash over v squared, where u is the numerator, v is the denominator. We get f double dash of x is equal to the derivative of 2x times 1 plus x squared minus 2x times the derivative of 1 plus x squared over 1 plus x squared in brackets squared. And that equals to 2 times 1 plus x squared in brackets minus 2x times 2x over 1 plus x squared in brackets squared. We can expand the brackets. We get f double dash of x is equal to 2 plus 2x squared minus 4x squared over 1 plus x squared in brackets squared. We have two like terms here, which we can combine. So we get f double dash of x is equal to 2 minus 2x squared over 1 plus x squared in brackets squared. Now, the denominator, 1 plus x squared in brackets squared, is positive for all real values of x. And the numerator, 2 minus 2x squared, is greater than 0 in the interval x greater than negative 1 and less than 1, since x squared is less than 1 in the given interval. Hence, the second derivative, f double dash of x, is greater than 0 or positive, since we're dividing a positive value by a positive value. That's positive, and we're dividing it by another positive, so we get a positive answer. In the interval x between negative 1 and 1, therefore f of x is concave up in the interval x greater than negative 1 and less than 1 as required. Part B. A table of function values, correct to 4 decimal places, for some x values is provided. Using the function values provided and the trapezoidal rule, estimate the shaded area in the diagram. From the table, the width h between consecutive x values is 0.25. Using the extended trapezoidal rule, the area A is estimated by area is approximately equal to 0.25 over 2, so that's our h over 2, times open bracket 0 plus 2 times 0.0606 plus 2 times 0.2231 plus 2 times 0.4463 plus 0.6931 close bracket, and that's approximately 0.2691375. But note that this is in the interval x between 0 and 1. But the question is asking for the area under the curve in the interval x between -1 and 1. Note also that f of x is even, hence the area is given by twice the value that we just found here. So that's 0.2691375 times 2, which is equal to 0.538275 square units. Therefore, the area under the curve in the interval x between -1 and 1 is estimated to be 0.538275 square units. Part C. Is the answer to Part B an overestimate or underestimate? Give a reason for your answer. From Part A, we found that the curve is concave up in the interval x between -1 and 1. And since the curve is concave up in the interval given, the trapezoidal rule will overestimate the exact area under the curve. And I can demonstrate that with the following diagram. Here's a sketch of y equals f of x, it's concave up. I've sketched a trapezium, which is part of the trapezoidal rule, and we can see here that the area of the trapezium overestimates the exact area under the curve from x equals a to x equals b. And I've shaded the overestimated area here. Question 23. A random variable is normally distributed with mean 0 and standard deviation 1. The table gives the probability that this random variable is less than z. The probability values given in the table for different values of z are represented by the shaded area in the following diagram. Part A. By calculating a z-score, find the percentage of scores that are between 58 and 70. The raw score of 58 corresponds to the mean, hence its z-score is 0. Now the z-score for the raw score of 70 is given by the z-score formula, which is raw score minus mean, in brackets, divided by the standard deviation. So 70 minus 58 in brackets divided by 15 is equal to 0.8. Now we want the percentage of scores that lie between a z-score of 0 and a z-score of 0.8. Now from the table, the percentage of scores below z equals 0.8 is 0.7881. So I'll just show the table there on the screen. So we have a z-score here of 0.8, and from the table, z equals 0.8 corresponds to 0.7881. That means 78.81% of scores lie below or to the left of z. But we want the percentage of scores that lie between z equals 0 and z equals 0.8. Just put the diagram back up on the screen. So we want the percentage of scores that lie between 0 and 0.8. Now we know from the characteristics of the standard normal distribution, half the scores lie to the left of 0, or a z-score of 0. So 0.7881, so that's this whole shaded area, if we take away 0.5, we get the percentage of scores that we want. So the percentage of scores between z equals 0 and z equals 0.8 is given by 0.7881 minus 0.5, and that equals 0.2881, or 28.81%. Part B. Explain why the percentage of scores between 46 and 70 is twice your answer to Part A. The z-score for the raw score of 46 is given by 46 minus 58 in brackets divided by 15, which equals negative 0.8. So we're just using the z-score formula that we used in Part A. Since the normal distribution, or the normal curve, is symmetrical about z equals 0, then the percentage of scores from z equals negative 0.8 to z equals 0.8 is twice the percentage of scores from z equals 0 to z equals 0.8. If we have a look at the normal curve, if that was z equals 0.8, then z equals negative 0.8 would be roughly here. And this area here from z equals negative 0.8 to z equals 0.8 would be twice the area from z equals 0 to z equals 0.8. Therefore, the percentage of scores between 46 and 70 is twice the percentage of scores between 58 and 70, which means it's twice the answer that we obtained in Part A. Part C. By using the values in the table above, find an approximate minimum score that a candidate would need to be placed in the top 10% of the candidates. Being in the top 10% of candidates implies being above the bottom 90% of candidates. If we just go back to our normal distribution, we want the bottom 90% to be in this shaded region here. Now looking at the table, the bottom 90% corresponds to a z-score of 1.3. In other words, candidates in the bottom 90% will score less than a z-score of 1.3. So being in the top 10%, a candidate will need to score above a z-score of 1.3. Later on, we'll need to convert that z-score into an actual or a raw score. So from the table, the bottom 90% of candidates will be below a z-score of 1.3. Now we need to find the raw score, or the actual score that corresponds to a z-score of 1.3. So we need to reverse the z-score formula that we used in Part A. So a z-score of 1.3 is equal to x minus 58 in brackets, where x is our raw score, divided by the standard deviation of 15. We're going to move this divided by 15 over to the other side, and it becomes a multiplication. So 1.3 times 15 is equal to x minus 58. Now 1.3 times 15 is 19.5. So the equation simplifies to 19.5 is equal to raw score minus 58. So isolating x, which is our raw score, we get x is equal to 19.5 plus 58, which equals 77.5. If we round that up, we get 78. Therefore, a candidate will need to score at least 78 to be placed in the top 10% of candidates. Question 24. Jack intends to deposit $80 into a savings account on the first day of each month for 24 months. The interest rate during this time is 6% per annum, compounded monthly. Part A. Calculate how much money Jack will have in his account at the end of 24 months. Jack will be depositing $80 per month over 24 months. This means the first deposit of $80 will be in the account for the full 24 months, earning interest. The second deposit will be in the account for one less month, so it'll be in the account for 23 months. So it's only going to earn 23 months worth of interest, and the pattern continuing for 24 months in total. Now we can model this using a geometric progression. We'll do that shortly. But firstly, we need the interest rate per month because the interest rate quoted was the interest rate per annum or per year. So to get the interest rate per month, we take the interest rate per annum, 6%, and we divide that by 12, and we get 0.5% or 0.005 as a decimal. So to get the future value, that's the amount in Jack's account at the end of 24 months, we use the following expression. We have $80 and we're going to increase that by 1.005 and we're going to raise that to the power of 24 because it's going to happen 24 times. That's that first deposit of $80 that's going to be in the account for the full 24 months. Then we're going to add on to that 80 times 1.005 to the power of 23 and so on until we get to the final month. So we're going to plus 80 times 1.005. So the last deposit of $80 is only going to earn 1 month's worth of interest. Now we can factorize out 80 and 1.005 from all the terms of this geometric series, and we get future value is equal to 80 times 1.005 times, open bracket, 1 plus 1.005 plus 1.005 squared plus ... plus 1.005 to the power of 23. So what I've done is I've just switched the terms around. So the term with the highest index or highest power now is at the end. Just makes it a lot easier to see. Now what we have here in brackets, so the last bracket here, this is a geometric series. First term A is 1 and a common ratio of 1.005. That's the R variable in the sum of a geometric progression formula. So future value is equal to 80 times 1.005 times 1 minus 1.005 to the power of 24, since there are still 24 terms in this series, over 1 minus 1.005. So that's the formula A times 1 minus R to the power of N over 1 minus R. And that evaluates to 2044.729201 and so on. So we need to round that to 2 decimal places because it's a money amount or a value in a bank account. Therefore, Jack will have $2,044.73 in his account at the end of 24 months, correct to the nearest cent. Part B. A table of future value interest factors could have been used to calculate how much money Jack would have in his account at the end of 24 months. Part of the table is shown. What is the value of A in the table? Give your answer correct to 3 decimal places. The table shown gives us the future value of an annuity of $1 per period over a number of periods for a given interest rate per period. Now from part A, we know that Jack deposits $80 per month over 24 months at 6% per annum, but it's 0.5% per month. And we know that the future value, or the amount in Jack's account at the end of 24 months, is $2,044.73. Now to work this out, I'm going to use the unrounded future value, that is 2044.72920. We know that this is based on an annuity of $80 per month. But the table is based on an annuity of $1 per month. So if we take this value here, which we found in part A, divide that by 80, we get the value of A that we want in the table, which is 25.559115. How we can interpret this value is if we deposit $1 per month over 24 months at 0.5% per month, compound interest, the future value of that would be 25.559115 $25,559,115 or $25.56 correct to the nearest cent. Therefore, A is equal to 25.559 correct to 3 decimal places. Question 25. A function f of x is defined as f of x equals 0 for x less than 0, f of x equals 1 minus x over h for x greater than or equal to 0 and less than or equal to h, and f of x equals 0 for x greater than h, where h is a constant. Part A. Find the value of h such that f of x is a probability density function. I'm going to present two different methods for finding the value of h. In the first method, I'm going to use integration to form an equation and then solve for h. In the second method, I'm going to use coordinate geometry without using any integration at all. But the end result is the same. Let's have a look at the first method, forming an integral equation. So we want to solve for h, the equation, the integral from x equals 0 to h of 1 minus x over h dx equals 1. Now it equals 1 because the sum of the probabilities must equal 1. Noting that h is a constant, integrating 1 minus x over h, we get x minus x squared over 2h from x equals 0 to h equals 1. Applying the limits of integration, we get h minus h squared over 2h. Now we can cancel a h here and a h there. Minus 0 equals 1. So that simplifies to h minus h over 2 equals 1. Now h minus h over 2 is equal to h over 2. So h over 2 equals 1, therefore h equals 2. The alternate solution involves coordinate geometry. Now if we look at the function y equals 1 minus x over h from x equals 0 to h, y equals 1 minus x over h is a linear function, straight line function with a negative gradient. Its y-intercept is 1, its x-intercept is h, and we have a right angled triangle. We want the area of the triangle to equal 1. So using the area of a triangle formula, half times base times height, we get half times h, that's the base, times the height of 1, and that equals 1. So half times h times 1 is h over 2, and that equals 1. And solving this equation, we get h equals 2. Part B. By first finding a formula for the cumulative distribution function, sketch its graph. To find the cumulative distribution function, the CDF, denoted by capital F of x, we integrate the PDF, 1 minus x over 2 from x equals 0 to x equals x. So integrating 1 minus x over 2, we get x minus x squared over 4 from x equals 0 to x equals x. Applying the limits of integration, we get x minus x squared over 4 minus 0. So the CDF, capital F of x, is equal to x minus x squared over 4, and it's defined in the interval x greater than or equal to 0 and less than or equal to 2. Now, capital F of x is equal to 0 for values of x less than 0, and capital F of x is equal to 1 for values of x greater than 2. Let's have a look at the graph of capital F of x. So here's the graph. Note that it's a concave down parabola in the interval x between 0 and 2. Notice that beyond x equals 2, it's a straight line, horizontal line, where y is equal to 1. And it's 0 to the left of x equals 0. Part C. Find the value of the median of the probability density function f of x. Give your answer correct to 3 decimal places. To find the median, we solve the equation capital F of x equals 0.5, where capital F of x is our cumulative distribution function that we found in part B. So x minus x squared over 4 equals 0.5. Multiplying all terms by 4 to eliminate this denominator here, we have 4x minus x squared equals 2. Moving all terms over to one side to form a quadratic equation, we get 0 is equal to x squared minus 4x plus 2. Using the quadratic formula, we get x is equal to 4 plus or minus the square root of negative 4 in brackets squared minus 4 times 1 times 2 over 2 times 1. So that's the formula negative b plus or minus the square root of b squared minus 4ac over 2a. And we get x is equal to 4 plus or minus the square root of 8 over 2. Now the square root of 8 can be simplified to 2 root 2. So x is equal to 4 plus or minus 2 root 2 over 2. Now we can divide all terms by 2. So x is equal to 2 plus or minus root 2. But we require x to be in the interval between 0 and 2. So x has to be greater than 0 and less than 2. Now 2 plus the square root of 2 is greater than 2. So we need to discard the solution x equals 2 plus the square root of 2. Therefore, the median is x equals 2 minus the square root of 2, which is approximately 0.586, correct to 3 decimal places. Question 26. 25 years ago, Phoenix deposited a single sum of money into a new bank account, earning 2.4% interest per annum, compounding monthly. Present value interest factors for an annuity of $1 for various interest rates, R, and numbers of periods, N, are given in the table. Phoenix made the following withdrawals from this account. $2,000 at the end of each month for the first 15 years, starting at the end of the first month, and $1,200 at the end of each month for the next 10 years, starting at the end of the 181st month after the account was opened. Calculate the minimum sum that Phoenix could have deposited in order to make these withdrawals. One way to solve this problem is to assume Phoenix made 2 withdrawals in the first 180 months, that is a withdrawal of $1,200 per month plus an extra $800 per month. And that gives us the $2,000 per month in the first 180 months, and that's equivalent to the first 15 years. Now from the 181st month onwards, Phoenix is only withdrawing $1,200 per month at the end of each month. So from the 181st month right through to the 300th month. So I've written that as 2 separate points. Phoenix withdrew $1,200 per month over 300 months, and Phoenix withdrew an extra $800 per month in the first 180 months. And we're going to treat this as 2 separate problems. So let's find the present value for the withdrawal of $1,200 per month over the entire 300 months. So going back to our table of interest factors, we want this column here, and we get that by taking the interest rate per annum, 2.4%, and dividing that by 12 because it's being compounded monthly, and we get 0.002. So we need to refer to this column here. And we want the present value for an annuity, we treat withdrawals as an annuity, over 300 months, so the interest factor is 225.430. So the present value is $1,200 per month, and we multiply that by 225.430, and we get $270,516. And I've labelled that with a letter A. Now, in the first 180 months, Phoenix is withdrawing an extra $800. And that's where we get the $2,000 from. $1,200 per month plus an extra $800 per month gives us $2,000 per month at the end of each month. So to find the present value for $800 per month over the first 180 months, going back to our table, we need this row here, and the interest factor is 151.036. So the present value is $800 multiplied by 151.036, and we get $120,828.80. And I've labelled that with a letter B. So to get the total present value, we take value A, add that to value B, and we get $391,344.80. And that's what Phoenix would have had to have deposited as a minimum to make those withdrawals. Question 27, Part A. Find the derivative of x squared tan x. Use the product rule to differentiate x squared tan x because we have a product of two functions of x. We have an x squared and we have a tan x. Now the derivative of x squared is 2x and the derivative of tan x is sec squared x. So the derivative of x squared tan x is equal to 2x times tan x plus x squared times sec squared x. And that's using the rule u dash v plus uv dash, where u is equal to x squared and v is equal to tan x. Part B. Hence, find the integral of x tan x plus 1 in brackets to the power of 2 dx. Start by expanding the integrand using perfect square expansion. So x tan x plus 1 in brackets squared is equal to x squared tan squared x plus 2x tan x plus 1. We can replace the tan squared x here using a Pythagorean identity, so we can express tan squared x in terms of sec squared x. So x tan x plus 1 in brackets squared is equal to x squared times sec squared x minus 1 in brackets, because that's equivalent to tan squared x, plus 2x tan x plus 1. Now we need to do this because from part A, we need to have a sec squared x appearing in the integrand. So expanding the brackets here, we get x squared sec squared x minus x squared plus 2x tan x plus 1. So if you recall from part A, when we differentiated x squared tan x, we ended up with a 2x tan x plus x squared sec squared x. And here they are. We have the x squared sec squared x appearing here and the 2x tan x appearing here. So the integral of x tan x plus 1 in brackets squared dx is equal to the integral of x squared sec squared x plus 2x tan x dx. If we go back to part A, if the derivative of x squared tan x is 2x tan x plus x squared sec squared x, then reversing this, if we integrate the right hand side, we go back to x squared tan x. So back to our integral here. The integral of x tan x plus 1 in brackets squared dx is equal to the integral of x squared sec squared x plus 2x tan x dx plus the integral of negative x squared plus 1. So that's the remaining two terms, this term here and this term here. And that's equal to x squared tan x from part A minus x cubed over 3 plus x plus the constant of integration c. Question 28. Anna is sitting in a carriage of a Ferris wheel which is revolving. The height, A of t, in meters above the ground of the top of her carriage is given by A of t equals c minus k times cos pi t over 24, where t is the time in seconds after Anna's carriage first reaches the bottom of its revolution and c and k are constants. The top of each carriage reaches a greatest height of 39 meters and a smallest height of 3 meters. Part A. Find the value of c and k. C represents the line of centre between the minimum height and the maximum height, and k represents the distance between the line of centre to either the maximum or the minimum height. So I've sketched this here as a visual reference. We can see that the minimum height is 3 meters, the maximum height is 39 meters. C is exactly midway between the minimum height and the maximum height. So the average of 3 and 39 is 21. And the distance between 21 and 39, or 21 and 3, is 18. And I've shown the working out here. C is the line of centre halfway between the two height extremes. Hence, C is equal to 39 plus 3 in brackets divided by 2, so it's an average. So C is equal to 21. And k is the amplitude of motion, which is the distance from the line of centre to either height extreme. Hence k is equal to 39 minus 21. Alternatively, it could be 21 minus 3. So k is equal to 18. Therefore, c is equal to 21 and k is equal to 18. Part B. How many seconds does it take for one complete revolution of the Ferris wheel? The time taken for one revolution, or one complete spin of the Ferris wheel, is equivalent to one period of motion. Now, the period, capital T, is given by 2 pi divided by the coefficient of the time variable t. So if you recall from the equation of A of t, we have A of t is equal to c minus k times cos of pi t over 24. So the coefficient of t here is pi over 24. So to find the period, we take 2 pi, we divide that by pi over 24. The 2 pi's will cancel, we multiply the 2 and the 24 together, and we get 48. Therefore, one revolution takes 48 seconds. Part C. Billy is in another carriage. The height, B of t, in meters above the ground of the top of her carriage is given by B of t equals c minus k times cos pi over 24 times t minus 6, where c and k are as found in part A. During each revolution, there are 2 occasions when Anna's and Billy's carriages are at the same heights. At what 2 heights does this occur? Give your answer correct to 2 decimal places. We want to find the times when both carriages are at the same height above the ground. So we want to solve for t, the equation A of t equals B of t. 21 minus 18 cos pi t over 24 equals 21 minus 18 cos pi over 24 times t minus 6. Now the two 21s will cancel. We can also divide both sides of the equation by negative 18. Also, we can take the inverse cos of both sides of the equation. So we're left with pi t over 24 equals pi over 24 times t minus 6. Multiplying both sides of the equation by 24, dividing both sides by pi, we get t is equal to t minus 6, and that's impossible. Now the next thing to consider is the even characteristic of the cosine curve. Recall that cos theta is equal to cos negative theta, since cos theta is an even function. So if we go back to the original equation, we can replace the angle here on the left-hand side with its negative. So we can save a few steps and we can go to this point here. So we can replace pi t over 24 with negative pi t over 24. And we get this equation here. So negative pi t over 24 equals pi over 24 times t minus 6. And that simplifies to negative t equals t minus 6. And we do get a valid solution, t is equal to 3. Now another property to recall is cos 2 pi minus theta is equal to cos theta. And I've sketched a cosine curve here. So if that's cos theta here, if we come back from 2 pi to the left-hand side, you end up at the same two heights. So the equation can be 2 pi minus pi t over 24 is equal to pi over 24 times t minus 6. Multiplying all terms by the denominator 24, we get 48 pi minus pi t is equal to pi times t minus 6. Dividing all terms by pi, we get 48 minus t is equal to t minus 6. Collecting like terms, we get 2t is equal to 54, so t is equal to 27, and that's our second solution. Finally, we need to find the heights at the times where t is equal to 3 and t is equal to 27, because that's what the question is asking for. So we can use a of t for that. So a of 3 is equal to 21 minus 18 times cos 3 pi over 24, and that evaluates to 4.37016 and so on. A of 27, that evaluates to 37.6298 and so on, but we need to round those values correct to 2 decimal places. Therefore, the two heights where both carriages are at the same height above the ground are 4.37 metres and 37.63 metres, correct to 2 decimal places. Question 29. Consider the curve y equals ax squared plus bx plus c, where a does not equal 0. At a particular point, the tangent and normal to the curve are given by t of x equals 2x plus 3 and n of x equals negative 1 over 2 times x minus 2 respectively. The curve has a minimum turning point at x equals negative 4. Find the values of a, b and c. The first thing we can establish is that y equals ax squared plus bx plus c is the equation of a concave up parabola, since it has a minimum turning point at x equals negative 4. Hence the value of the leading coefficient a is positive or greater than 0. If it had a maximum turning point instead, then a would be negative. Now we can solve t of x equals n of x, since t of x is the equation of the tangent to the parabola and n of x is the equation of the normal to the parabola, and they both pass through the same point and contact the parabola at the same point. By solving this equation, we can get the coordinates of the point of contact with the parabola, and that also gives us the coordinates of a known point on the parabola, which will be useful later on. So solving 2x plus 3 equals negative 1 over 2 times x minus 2, multiplying all the terms by the denominator 2, we get 4x plus 6 equals negative x minus 4. Moving all the x's over to the left-hand side and the constants over to the right-hand side, collecting the like terms, we get 5x equals negative 10, so x is equal to negative 2. And when x equals negative 2, t of negative 2, so I'm just using this equation here to find the corresponding y-coordinate, we get negative 1. Hence, negative 2 comma negative 1 is a point on the parabola y equals ax squared plus bx plus c. Now the x-coordinate of the vertex is at x equals negative 4, since the vertex is the minimum point on the parabola. Hence, negative b over 2a equals negative 4. We can rearrange this equation to express b in terms of a, and we get b equals 8a. We'll call this equation number 1. Differentiating y equals ax squared plus bx plus c to obtain the gradient function y dash, we get y dash is equal to 2ax plus b. Now, at x equals negative 2, the gradient of the tangent is 2. If you recall, the equation of the tangent was given as tx equals 2x plus 3 at a particular point on the parabola. We know what that particular point is now. It's the point negative 2 comma negative 1, which we found earlier. So at x equals negative 2, the gradient of the tangent is 2. Hence, 2 equals 2a times negative 2. So I've substituted x equals negative 2 here, plus b. But we've found up here that b equals 8a. So we can replace the b with 8a. So now we have an equation with one type of variable. 2 equals negative 4a plus 8a. So 2 is equal to 4a. So a is equal to 1 over 2. Now from equation number 1, if a is equal to 1 over 2, that means b must equal 4. So we have two of the known variables already, a and b. So we just need to find the variable c. Now we know from before that the point negative 2 comma negative 1 lies on the parabola. We have the value of a and b now. We just need to find the c. So y is equal to 1 over 2 x squared plus 4x plus c. Substituting x equals negative 2 for the x variables here, and y equals negative 1 for the y variable here, we get negative 1 equals half times negative 2 in brackets squared plus 4 times negative 2 plus c. We can evaluate this term here and this term here. We get negative 1 is equal to 2 minus 8 plus c, and 2 minus 8 is negative 6. If we move that over to the other side, it becomes positive 6. 6 minus 1 is 5, so c is equal to 5. Therefore, a is equal to half, or 1 over 2, b is equal to 4, and c is equal to 5. Question 30. Suppose the geometric series x plus x squared plus x cubed and so on has a limiting sum s. By considering the graph y equals negative 1 minus 1 over x minus 1, or otherwise, find the range of possible values of s. The first term of this geometric series is x, and its common ratio is also x. Using the limiting sum formula, a over 1 minus r, where a represents the first term of this geometric series and r represents the common ratio, we get s is equal to x over 1 minus x for values of x between negative 1 and 1, not including the endpoints. Now we need to rework this limiting sum equation. And we need to rework it in such a way to make it easy to graph so that hopefully we can see the possible values of s, which is what the question is asking for. Now the question does give us one clue. It asks us to consider the graph of y equals -1 minus 1 over x minus 1. Now if we go back to our limiting sum equation, we can see that the denominator is 1 minus x. Now if we can rework this equation so that the denominator is x minus 1, hopefully we can get the equation that we want, make it easy enough to graph, and then hopefully we can see the values of s that are possible. So starting off with the numerator x, subtract 1 and then add 1. Now subtracting 1 and then adding 1 in effect does nothing. So -1 plus 1 is equal to 0. So we haven't changed the equation. But what we have done is to make it in a form that we can express this single fraction as a sum of two fractions with a common denominator of 1 minus x. So splitting this fraction up, we get s is equal to x minus 1 over 1 minus x plus 1 over 1 minus x. Now this one here is this one here. Factorising out -1 from the numerator in the first fraction, we get negative bracket 1 minus x close bracket over 1 minus x. And 1 minus x over 1 minus x is 1. Multiplying it by -1, the value of this fraction here is -1. And with the second fraction here, multiplying top and bottom by -1, we get a numerator of -1 and a denominator of negative bracket 1 minus x close bracket. Multiplying through the negative in the denominator, the 1 minus x becomes x minus 1. So we get s is equal to -1 plus -1 over x minus 1, which simplifies to s equals -1 minus 1 over x minus 1, which is identical to the equation that was given in the question that we were asked to consider in the first place. So we can graph s equals -1 minus 1 over x minus 1, and hopefully we can see the range or the values of s that are possible. The graph of s is a hyperbola with vertical asymptote at x equals 1, horizontal asymptote at y equals -1, and it passes through the origin. Now we know that by letting x equal 0 and evaluating this expression here. -1 minus 1 over 0 minus 1, we get -1 plus 1, which is equal to 0. So the graph passes through the origin. Now it also helps to have another point on that graph. If we let x equal -1, so substitute -1 here, -1 minus 1 over -1 minus 1, we get s is equal to -1 over 2, or -half. And I've marked that point here as well. So sketching the axes with a ruler, I've sketched in the asymptotes as well using a dashed line. And the hyperbola will look something like this. Now we know that x has to be a value between -1 and 1, and that was established earlier on. So the values of s that we're interested in have to be in the interval where x is greater than -1 and less than 1. So from the right hand side of this point here, we can see that s starts off at -1 over 2, but it can't include -1 over 2, and s approaches infinity as x approaches 1. So from the graph of s, it can be deduced that possible values of s are greater than -1 over 2. Question 31. Two circles have the same center O. The smaller circle has radius 1 centimeter, while the larger circle has radius 1 plus x centimeters. The circles enclose a region QRST, which is subtended by an angle theta at O as shaded. The area of QRST is a square centimeters, where a is a constant and a is greater than 0. Let p centimeters be the perimeter of QRST. Part A. By finding expressions for the area and perimeter of QRST, show that P of x equals 2x plus 2a over x. Consider area QRST. So here's the diagram showing the shaded region, which is the area QRST. It's the difference between the large minor sector QOR and the small minor sector TOS. So it's sector QOR minus sector TOS. Now the radius of sector QOR is x plus 1 and the radius of sector TOS is 1. So area QRST is equal to area of minor sector QOR minus area of minor sector TOS, using the half r squared theta formula, which gives us the area of a sector with radius r and angle theta in radians subtended at the center of the circle. We get half times x plus 1 in brackets squared times theta minus half times 1 squared times theta. Now I'm not going to expand this just yet, but we know that half times 1 squared times theta is just half theta. Now we can factorize out half theta from this term and this term. So A, which represents the area QRST, is equal to half theta times open bracket x plus 1 squared minus 1 close bracket. We'll call this equation number 1. Now consider the perimeter of QRST. And the perimeter is made up of minor arc QR plus minor arc TS plus QT plus RS. Now RS is equal to QT, so it's equal to X. And we can use the formula for the arc length of a circle with radius R and angle theta, which is arc length equals theta times R. So perimeter QRST is equal to minor arc QR plus minor arc TS plus QT plus RS, which equals x plus 1 in brackets times theta. So this is the radius of the large minor sector, plus 1 times theta, plus x. Now collecting like terms and factorising out theta from this term and this term, we get P of x, which represents the perimeter of QRST, equals theta times x plus 2 plus 2x. Now if we factorise out theta from here and here, we have x plus 1, which is where this x plus 2 comes from. We'll call this equation number 2. If you look at what we're asked to show in part A, we're asked to show that P of x equals 2x plus 2a over x. Notice that there's no theta variable here. And that's a strong clue. What we need to do is somehow use equations 1 and 2, effectively solving them simultaneously by eliminating theta. So from equation number 1, so this is our area equation, I'll just go back to that. What we want to do is make theta the subject and then substitute that for theta in equation number 2, which effectively eliminates theta, and then we have P of x in terms of x without using theta at all. So from equation number 1, I've started off by multiplying both sides of the equation by 2. So we have 2a equals theta times open bracket x squared plus 2x plus 1. So I've expanded the x plus 1 squared using perfect square expansion, and then minus 1 close bracket. So I'll just go back to the original equation. I just expanded this here, x plus 1 in bracket squared, x squared plus 2x plus 1 minus 1. So 1 minus 1 will cancel, become 0. So we have 2a is equal to theta times open bracket x squared plus 2x close bracket. And we can factorise out x from what's inside the brackets here from these two terms. So we get 2a is equal to theta x times x plus 2 in brackets. Now we could make theta the subject. So dividing the 2a by x times x plus 2 in brackets, we get theta is equal to 2a over x times x plus 2 in brackets. So from equation number 2, I'll just go back to equation number 2 here. we have p of x is equal to theta times x plus 2 in brackets plus 2x. We now have an expression for theta. Theta is equal to 2a over x times x plus 2 in brackets. So substituting 2a over x times x plus 2 in brackets for theta, we get p of x is equal to 2a over x times x plus 2 in brackets times x plus 2 in brackets plus 2x. Now this denominator x plus 2 will cancel with x plus 2 here. So we're just left with 2a over x plus 2x. Therefore, p of x equals 2x plus 2a over x as required. Part B. Show that if the perimeter p of x is minimized, then theta must be less than 2. Part B mentions minimizing the perimeter. So we'll need to differentiate the perimeter equation p of x equals 2x plus 2a over x that we found in Part A, find any stationary points and test those stationary points to make sure that they are in fact a minimum point. To make the differentiation a little easier, we'll express the second fraction here using a negative index. So p of x is equal to 2x plus 2 times a times x to the power of negative 1. Differentiating p with respect to x, we get p dash of x is equal to 2 minus 2 times a times x to the power of negative 2. And because we need to test any stationary points, we need the second derivative. So differentiating p dash of x with respect to x, we get p double dash of x is equal to 4 times a times x to the power of negative 3. Now note that the second derivative, p double dash of x, is greater than 0, or positive, since a is greater than 0, because a represents an area, and x is greater than 0 because x represents a distance. So any stationary points that we find will be minimum points. So to find any stationary points, we solve p dash of x equals 0. So 0 is equal to 2 minus 2 times a times x to the power of negative 2. The equation can be written using positive indices now. 0 is equal to 2 minus 2a over x squared. Dividing all terms by 2 to simplify the equation, we get 0 is equal to 1 minus a over x squared. Multiplying all terms by x squared to simplify the equation further, we get 0 is equal to x squared minus a. Rearranging this equation to isolate x squared, we get x squared is equal to a. And taking the square root of both sides, we get x is equal to the square root of a. And we only consider the positive square root because x is positive. Now p of x is a minimum when x is equal to the square root of a, since the second derivative, p double dash of x, is positive as mentioned earlier on. Now from Part A, theta is equal to 2a over x times x plus 2 in brackets. But we have a value for x now. X is equal to the square root of a. So substituting the square root of a for x, we get theta is equal to 2a over the square root of a times the square root of a plus 2 in brackets. Expanding the brackets, we get theta is equal to 2a over a plus 2 times the square root of a. Now since a is positive, or a is greater than 0, then 2a over a plus 2 times the square root of a must be less than 2a over a. If the numerators are identical, but we make the denominator of one of the fractions bigger, this makes that whole fraction smaller in value. So because the fraction on the left-hand side has a larger denominator than the fraction on the right-hand side, this fraction here is smaller than this fraction here. Now 2a over a will simplify to 2 because the a's will cancel. So 2a over a plus 2 root a is less than 2, and 2a over a plus 2 root a is equal to theta. Therefore, theta must be less than 2.